So we're still in 8.5. Now we're looking at what if you have a quadratic factor in your denominator that is not factorable. So it would be called an irreducible quadratic factor. So the only thing that really changes is when you set up that fraction, the numerator could be something that is linear or degree 1. So that just slightly changes the setup for your decomposed fraction. So let's start by doing the steps here. Step 1 is to always factor the denominator. So I'm looking at this denominator and I'm noticing that it is a difference of cubes. So I'm factoring a difference of cubes here. So for a same, opposite, always positive. Alright, so that quadratic factor, x squared plus x plus 1, that is not factorable. So we can't really go any further than that as far as factoring goes. So let's go ahead and write out what we want. So here's step 2. So we want to decompose this fraction as a sum of fractions with simpler denominators. So my first one will have, it really actually doesn't matter what order you put it in, but I'm trying to keep it consistent with the way it's written here on step 2. It could have up to a linear numerator, so I'll write ax plus b. So I will need to solve for the a and the b value. And then the second fraction will look similar to what we've been doing in the previous examples. So the next step in this process is also the same, and that is to multiply by the LCD on both sides. So the LCD is x minus 1 times x squared plus x plus 1. That will be distributed over here. And then this will cancel out all of my denominators. Okay, so over here the entire denominator cancels. And on the right hand side it cancels differently with each one. X minus 1, so ax plus b times x minus 1 plus c times x squared plus x plus 1. So I need to solve for a, b, and c. I do have a linear factor of x minus 1, so I want to start off by plugging in x equals 1. That will zero that out, and I'll be able to solve for c. So I have 2 times 1 plus 4 equals a times 1 plus b times 1 minus 1, which is 0. That was the whole point of choosing 1. So this is 0 here. So I have 6 equals c times 3. So divide both sides by 3, and I have that c is equal to 2. Okay, so I don't have any other linear factors, but I am noticing here that I have a times x. So if I let x be equal to 0, and additionally replace c with 2, I should be able to solve for b. So that will be my next step. Let x equal 0 and replace c, now that we know what c is. So I have 2 times 0 plus 4 equals a times 0 plus b times 0 minus 1 plus 2 times 0 squared plus 0 plus 1. 4 equals, so a times 0 is 0, so b times negative 1 plus 2. Okay, subtract 2 from both sides. 2 equals negative b. Divide by negative 1, so b is equal to negative 2. Okay, so we still need to solve for a. We can do that by plugging in anything for x that we want, other than 0 or 1. We've already used those. Those won't do us any good. And then also replacing b and c with their now known values. So I think I will replace x with 2. I was thinking maybe negative 1, but I think I'll go with 2. Why not? So let's let x equal 2 and replace b and c. So I'll have 2 times 2 plus 4 equals a times 2 plus b. Oops, b is negative, so I'll do minus 2 times 2 minus 1. That's kind of the reason I picked 2 right there. C is 2. 2 squared plus 2 plus 1. Okay, so let's go ahead and continue simplifying this. So I have 2 times 2 plus 4. That's 8. This is 2a minus 2 times 1, so that doesn't change it at all, plus 2 times 2 squared is 4. 4 plus 2 is 6. 6 plus 1 is 7. So 14. So I have 8 equals 2a plus, what is that, 12. Subtract 12 from both sides. Negative 4 equals 2a. So a is also negative 2. Okay, so as usual, our last step is also to write out our decomposed form of our fraction. So that's the last thing we're going to do. So it was ax plus b, so negative 2x minus 2 over our quadratic factor, plus c over our linear factor. And that would be the answer. That is the decomposed form. We do have one more case we're going to look at, and that is what if that irreducible quadratic factor had been repeated. So this is the most complicated version that we'll be looking at in this class. It is very similar to the case with the repeated linear factors, but the one thing that is different is that, of course, the numerators are linear, and then you see that repetition down here in the denominator. In this sort of setup, there's a lot of subscripts. I would tend to not use subscripts. They're difficult to work with. I'll just use different letters. So here we see a fraction that already is factored in the denominator. We see x squared plus 16, which is not factorable, and we see that it's squared. So let's set up our decomposed form. So I want to be able to rewrite this fraction as the sum of simpler rational expressions. So one of them will have a single factor of x squared plus 16. The other one will have the two factors of x squared plus 16. So this is because we don't know exactly what it looks like, so we just cover all of our bases. We also don't know quite what the numerators will look like, but they could be up to degree 1. So I'll call this one ax plus b, and I'll call this one cx plus d. Okay, now the next step is the same as all the previous examples. We would multiply by the LCD, which is x squared plus 16 squared, which I will distribute here, and then multiply by the single fraction on the left-hand side. So this should be able to cancel out all of the denominators. So I'll have ax plus b times x squared plus 16 plus cx plus d. So notice that the denominator here also was canceled out. So there's a lot of things to solve for here. I don't really have anything that I can plug in to zero anything out. So I think what I'm going to do is show you a different process that you can use in a case like this where it's not really possible to plug in something to zero out a linear factor. The process I'm going to use is called equating coefficients. Let me write that over here. This, once again, is an identity, and it looks like it's a polynomial equal to a polynomial, true for any value of x, which would mean those polynomials should have the same coefficients. So what I'm going to do on the right-hand side is I'm going to FOIL out and combine like terms. So ax plus b times x squared plus 16, I get ax cubed, so first outer, plus 16ax inner, plus bx squared last, plus 16b, plus cx plus d. Now I'm going to rearrange the terms so that I can combine like terms. So for my degree 3 terms, I just have ax cubed. Then for my degree 2 terms, I just have bx squared. Now for linear terms, I have 16ax plus cx. So I have plus 16a plus c times x. And then for my constants, I have 16b plus d. So I'm going to start by looking at just the degree 3 terms. Here I have x cubed, here I have ax cubed. So equating coefficients tells me that these terms should have the same coefficients. This doesn't have a coefficient, so it's understood to be 1, so a must be equal to 1. Okay, so that's kind of powerful because I can now replace this with a 1. So let's go ahead and rewrite it with the replacement. So a I know is as 1, so x cubed plus bx squared plus, so 16 times 1 is 16, 16 plus c times x plus 16b plus d. Okay, now a couple more things to note. First of all, on the left-hand side, there are no degree 2 terms. So I'm looking here at bx squared. There is no x squared over here, or is there? There's no x squared, so really there's 0x squared. You know what? I think I want to rewrite this left-hand side to show you something. I'm going to write it as x cubed plus 0x squared plus 0x plus 1. I'm not trying to make it look more confusing, but there is no x squared term, but if you had to write one, its coefficient would be 0, right? So this is telling me right now that b is equal to 0. So I have a couple of them to solve for. Okay, so similarly, there is no linear term on the left-hand side. So if I had to write one, I'd have to write 0x. This is telling me that 16 plus c is equal to 0. So if I subtract 16, I get c equals negative 16. Okay, and the last thing that I'm seeing is the constant. So over here on the left-hand side, I do have a constant term. It's 1. So the constant term here is 16b plus d equals 1. But we already know that b is 0, so this means that d equals 1. So now we have all 4 of them, a, b, c, and d. We used a different process this time because we didn't have the convenient linear factors like we did last time. So we used equating coefficients, and we got them all. So let's write out our decomposed form of our rational expression. So it's ax plus b, a is 1, so b is 0, over x squared plus 16, plus, and then cx plus d, so negative 16x plus 1 over x squared plus 16 squared.